In this video, we're going to be looking at using differentiation, or the idea of differentiation, the idea of a derivative, to find a Taylor series for a function. We're going to start with the function f of x equals 1 over the quantity x minus 3 squared. We'll find its Taylor polynomial based at b equals 0, and then we'll find an interval for which it converges. This is example 5.6 in your course pack. Now, the trick in this one is really pretty clever, I think. Let's start with the function -1 over x minus 3 and take its derivative. We could use the quotient rule. I think I'll use the quotient rule. Why not? The way I remember that is low d high, the derivative of the numerator, minus high d low, the derivative of the denominator, all over the square of what's below. That's low d high minus high d low all over the square of what's below. I know, it's silly, but that's how I remember it. It works for me. What can I say? All right, now the derivative of a constant is 0, so that term goes away. This term goes to 0. And then we have minus a negative here, so we're going to have plus, or positive. And then the derivative of x minus 3 is just 1. And the denominator is x minus 3 squared. And that is exactly the function we're trying to find the Taylor series for. We know that -1 over x minus 3 can be written as the sum, as I goes from 0 to infinity, of x to the I over 3 to the I plus 1. And we know that just from a previous result. We did a problem a while ago that gave us this result. So knowing that, let's write 1 over the quantity x minus 3 quantity squared is equal to the derivative of -1 over x minus 3, and that is equal to the derivative of the sum, as I goes from 0 to infinity, of x to the I over 3 times I to the power of I plus 1. Now what I've got here is the derivative of a sum of several terms. And just as a reminder, if you have, I'm going to make up a few terms here, x squared plus 3x plus 2x cubed minus 7. That's a sum of terms. The derivative of this sum of terms is just the derivative of each term. In other words, the derivative of a sum is the sum of the derivatives of the terms. dx 2x cubed plus and so on, right? So one way to say this is that the derivative of a sum of terms is equal to the sum of the derivatives of the terms. This is a derivative of a sum of terms, so that's going to be equal, I'm going to erase this bottom line here, the derivative of the sum is going to be equal to the sum of the derivatives of the terms in the sum. Okay, now that, if you had, x to the 7th, and then the next one was x to the 6th, the next to the 5th, and so on, this is a polynomial. The denominator here is 3 to some power. When I is 0, it's 3 to the 1. When I is 1, it's 3 to the 2. When I is 2, it's 3 to the 3, and so on. So the denominator here is just a constant. The numerator is I to the 1, I to the 2, or sorry, x to the 1, x to the 2, x to the 3, and so on. So really all I'm doing is taking the derivative of a polynomial, and a polynomial is made up of multiple terms, but I can take the derivative of all of its terms at once by using this sort of formula, right? Let's start by rewriting this as the derivative of 1 over 3 to the I plus 1 times x to the I. Then when I take that derivative, I have a product now. I have this first factor times this second factor. So I'm going to have the first times the derivative of the second. The first is 1 over 3 to the I plus 1 times the derivative of the second is just x to the power of I. The derivative of that is I times x to the power of I minus 1. And that's how we take derivatives. And then I can rewrite this as, it looks like I have I over 3 to the I plus 1 times x to the I minus 1. Now, it's nice to have our x factor here just be x to the I. So let's use a different dummy variable. Let's call it j, and let's say j. I said j there, and I wrote I again. Let's make it k. Let's let k equal I minus 1. Then everywhere I see an I minus 1, I can replace that with k. Equally, if I have an I, if I add 1 to both sides of this, I is equal to k plus 1. So rewriting this gives me the sum of I. Now I gets replaced with k plus 1, so I have k plus 1 over 3 to the power of I plus 1. Well, I is k plus 1, so I have k plus 1 plus 1, or k plus 2, and then I have x to the power of I, which is k plus 1, minus 1. So that's just x to the k. And that puts my x, my index, right? K goes from, I'll say 0 for now. We'll come back to that in just a second. This x factor is the thing that's starting at the lowest value of k and going on from there. Now, when I changed my variable here, not my variable, my dummy, my index, I should have changed it down here as well. Since I goes from 0, when I is 0, k is negative 1. So technically, I should start at negative 1. But watch what happens when I plug in negative 1. I get negative 1 plus 1, which is 0. 0 over anything is 0, and 0 times anything is 0. So in this case, it happens that I can get away with starting my index at 0, even though that index is based on a substitution. Okay, so that's something to kind of keep in mind. So this is the Taylor series for 1 over x minus 3 quantity squared. This thing is equal to that thing on the right interval. Remember, we have to consider the interval of convergence. Well, this thing is based on the function negative 1 over x minus 3, and we know from a previous result that the interval of convergence for this is negative 3 to 3, also known as negative 3 to 3, also known as the distance from x is equal to 3. This is another, sorry, the distance from x is less than 3. This is another equally convenient, equally equivalent, and equally valid way to write this. These have the same meaning, right? It's symmetrical around 0, so that lets us get away with that. But that's the interval of convergence for this. Because the function we were actually working with is the derivative of the other function, the function we sort of borrowed from a previous result, the interval of convergence is the same. So here's my interval of convergence in any of the forms that you see here, whatever is your preference. My personal preference is for interval notation, but depending on the context, either of these others might work as well. Now, the big takeaway here, not just from this video, but from the end of the other one as well, is that anytime you have a rational function, remember the previous rational function was something like, well, it was a quadratic over a linear times, the numerator was a quadratic, the denominator was a linear times a quadratic, which made it a cubic. That was a rational function as well. And we used partial fraction decomposition to set that one up, but then we used the idea that the summation of two functions, the sum sigma of f plus g, is equal to or is equivalent to the summation of f plus the summation of g. So we used that idea together with partial fractions. In this example, we still have a rational function, and this the idea that this function, this specific function here, has this Taylor series associated with it, that it's equal to this Taylor series, that comes from a previous result. Here we used the result as we found it earlier, but to find this summation, or to find this Taylor series in the first place, we used the idea that we knew the summation for 1 over 1 minus x. That's the sum as I goes from 0 to infinity of x to the I. But that's only true between -1 and 1. So in any case, when you have a rational function like this, or like the bigger one that we had in the previous example, you can use combinations of 1 over 1 minus x to get your ultimate answer to the function that you're given. What is its Taylor series? You can also use integration in the way that we recognized here that the function we were given was the derivative of another function, right? We can use integration as well. We can take the fact that a known function is the integral of another function. So let's take a look at that example. That's going to be example 5.7, and we'll do that on the next screen. So here we are. This is example 5.7. We're going to be finding a Taylor series expansion for this function, arctangent, tangent inverse or arctangent. It's based at b equals 0, which makes it a Maclaurin series. And we're going to find its interval, or an interval on which it converges. We're going to find a radius or an interval of convergence. We'll start by taking the derivative of arctangent. And that's 1 over 1 plus x squared. And we know from a previous example that this is equal to the sum, as I goes from 0 to infinity, of negative x squared to the power of I. And that can be written as the sum as I goes from 0 to infinity of -1 to the power of I times x to the power of 2I. Now, we didn't do this example together, but it's based again on this is a rational function. It's based on finding a way to change this function into something that looks like this function. And in that case, I commented, I didn't do this, sorry, I didn't do the example like this, but I commented at the time that you had to be careful as you were reading through and trying that problem for yourself, that you also had to introduce a negative, right? I don't know if you remember that. Let me see if I can find what example number that was. That was example 5.4. Okay, so when you're watching this video and you're not sure how I'm getting from here to here to here, it's based on what we did in example 5.4. So go back and take a look at that. Now, so we can write the tangent inverse of x is equal to the integral of the derivative of the tangent inverse of x. That's just the fundamental theorem of calculus. and dx, but that's equal to, from 0 to x, the integral of 1 over 1 plus x squared dx. Now we have to be careful here because we can integrate this. It's arctangent, right? The answer here is arctangent, but that's not going to give us a summation. It's not going to give us a Taylor series. So we have to think now of this as the integral is equals the integral from 0 to x of the summation of this thing, and we did this up here, the summation of 1 over 1 plus x squared. The Taylor series for this is either this expression or this expression. And I'm going to use the second of those two expressions. So I'll write this as the integral of the summation as I goes from 0 to infinity of negative 1 to the power of I times x to the power of 2I, and then dx. So what I've done here is rewritten this expression as its summation. And I still have the bookends of an integral symbol and a dx, either side of that. Well, now what I have is the integral of a sum, and that's equal to the sum of an integral. Just like the derivative of a sum of terms is the sum of the derivative of those terms, the integral of a sum of terms is the sum of the integrals of those terms. So I can use this, put my integral inside. I get negative 1 to the I, x to the 2I, dx, and then I can integrate. But what I'm integrating is just this piece, right? Here's my integral. I'm going to include my dx there. Right? Notice that the summation there is now kind of on the outside. So what is the integral of negative 1 to the I times x to the 2I? Well, when you integrate, you bring the constant out front. So I'll just put that there. And notice that we're integrating with respect to x. So I have x to the power of 2I. When I integrate that, I get x to the power of 1 more than that. But then I have to divide by that new power. And of course, there are different ways to write this expression. We could write it as we have it here, or as I've done before, I could write it so that the factor with the x in it is a little bit more isolated. So I can write it like this, times x to the power of 2I plus 1. And this is the Taylor series for arctangent. If you are the kind of person who likes to keep collections of things, or if you have a note card with results on it that you feel like you might want to use, and by the way, the final exam for this course, you will be allowed to use a note card, so you can use your notes. This would be a good one to add. You have that the tangent inverse of x is equal to this Taylor series, this summation. That's another nice result to include on your note card. So now we've talked about how to use both differentiation and integration to find Taylor series for functions when the function itself may not be obvious or may not be very nice, but it's either its derivative or its antiderivative is something that we can either recognize right off the bat or that we can manipulate into something that we can recognize. Now, to finish this section, or to finish this video out, I do have one more type of problem to do, and I'll do that in a separate video. But to finish this video out, I want to point out and remind you, it's not really a reminder, we haven't really talked about it yet, that if you can find the interval of convergence for a function, for a Taylor series, then the interval of convergence for the integral of that Taylor series, or in fact the interval of convergence for the derivative of that Taylor series, will be the same. So if I can find the interval of convergence for the Taylor series associated with this function, which is this Taylor series right here, then I will be able to use it to find the interval of convergence for the integral of that series, which is this result down here. So what is the interval of convergence for this Taylor series right here. Well, our work in the example, what did I decide it was? I think 5.4, that was a problem like this, suggests that our interval of convergence would be x is less than 1. If that's true, then the interval of convergence for this series is also the absolute value of x is less than 1. This can be written as -1 is less than x is less than 1, or it can be written as the interval from -1 to 1. Any of those will work. So that's our interval of convergence for this series. Now, sometimes a function can't be integrated explicitly, but we can still use the idea that the integral of a sum is the sum of the integral. For example, well, I'll start this one on the next screen. Okay, in this problem, we're asked to find the Taylor series expansion based at b equals 0 for f of x equals the integral of e to the negative x squared. Well, we're asked to find the Taylor series expansion here because what we really probably wanted to do in this case was integrate e to the negative x squared. But we can't do that directly. That's not a problem we can do using just integration techniques. So instead of integrating e to the negative x squared, we're going to use Taylor polynomials to approximate the function that is the integral of e to the negative x squared. We'll start by reminding ourselves that e to the negative x squared, we'll start with e to the u. E to the u can be written as the sum, as I goes from 0 to infinity, there we go, of u to the power of k over k factorial. But our u in this case is negative x squared. So we have negative x squared to the power of I all over I factorial. And then I'll move my dx in a little bit. I'm integrating from 0 to x. Now the integral of a sum is the sum of the integral. So I can rewrite this as the sum, as I goes from 0 to infinity, of the integral, negative x squared to the power of I over I factorial dx. I'll do some algebra on this term here. Instead of negative x squared to the power of I, I'm going to think of this as -1 to the power of I times x squared to the power of I, and then I'll rewrite it again as -1 to the power of I times x to the 2I. So that's what I'm going to do in this next step here. Just rewrite that. I messed up here. This should be from 0 to x, not from 0 to infinity. Okay, so I can carry on now. I'm going to rewrite that integrand as -1 to the power of I times x to the power of 2I all over I factorial dx. And now we can integrate. So I'm working now inside here. I'm taking this integral. That's the next step I'm going to do. Notice that I factorial is a constant. -1 to the power of I is going to be a constant. And then x to the power of 2I integrates as x to the power of 2I plus 1 divided by the new exponent 2I plus 1. And I can rewrite this as, if I want to, the sum, as I goes from 0 to infinity, of -1 to the power of I over 2I plus 1 times I factorial times x to the power of 2I plus 1. That gets that x, the factor that with the x in it, kind of by itself here. That's what we've been aiming for. So this is my Taylor series for e to the negative x squared. Now that's the Taylor series. That's what we were asked for initially, find the Taylor series expansion. But then they asked us to write out the first 5 terms of the series. So let's do that. And I'll do it down here. Notice that I'm starting at I equals 0. So I have negative 1 to the power of 0 over 2 times 0 plus 1 times 0 factorial times x to the 2 times 0 plus 1. That's my first term. That's the term I get when I equals 0. That's going to be anything to the 0 power is 1, except for 0, but that's not the problem here. I have 1 over 1 times 1, 0 factorial is 1, times x. So my first term is just x. My second term comes about when I equals 1. So I get negative 1 to the power of 1, which is negative 1, over 2 times 1 plus 1, which is 3, 1 factorial, and x to the power of 2 times 1 plus 1, or 3. So my second term is actually going to be a negative, so I'll write it as minus x cubed over 3 times 1 factorial. My next term, this is my third term, will be when I is 2, I get negative 1 to the power of 2, which is positive 1, over 2 times 2 plus 1, which is 5, times 2 factorial, times x to the 5. So my third term is x to the power of 5 over 5 times 2 factorial. 2 factorial is just 2 times 1, or 2, and 5 times 2 is 10. Now I've run out of room, so typical for me. Let's go down here. Plus, I have to do 5 terms. I've got 3 so far. 1, 2, 3. I need 2 more. So I have I equals 0, I equals 1, I equals 2. I need I equals 3 and I equals 4. When I equals 3, I get negative 1 to the power of 3, which is negative 1. 2 times 3, which is 6, plus 1 is 7, times 3 factorial, times x to the 7th. I'm getting the same numerical answer value here as I do here, right? 2i plus 1, 2i plus 1. Once I figure out what this one is, this one's the same. So I have, for my fourth term, I have a minus x to the 7th over 3 factorial is 3 times 2 times 1, which is 2 times 1, the previous factorial, that's 2, times the next integer, 3. So that's 6. And 6 times 7 is 42. So that's my fourth term. And my fifth term is going to be, let's see, I have 0, 1, 2, 3, 4. When I equals 4, this is positive. I get 8 plus 1 is 9, 4 factorial. So I'm going to have 1 over, what did I say, 4. 8 plus 1 is 9 times 4 factorial times x to the power of 9. So I'll get a plus x to the 9th. I'm going to have to erase my arrow here. X to the 9th over, well, 3 factorial was 6, so 4 factorial is 4 times that. That's 24. 24 times 9, off the top of my head, I don't know. 4 times 9 is 36. 2 times 9 is 18, so that's 180. So 6, 11, 216. So I have over 216. Now, I don't care if you do this arithmetic. You could just leave that as 9 times 4 factorial if you want. That would be fine with me. But those are the first 5 terms. Now, the course pack actually asks you to give 5. In the example, they say give the first 5 terms, but then they only work out the first 3. So I think that's interesting. Right, so that is another example of, or this is an example of finding the 5 terms, first 5 terms explicitly of the Taylor series, in fact the Maclaurin series, for the function that is the integral of a function. And we did that because we might have wanted to integrate this function, but we can't, so we approximate it by finding its Taylor series, not the Taylor series of the function, but the Taylor series of the integral of the function. The Taylor series of the integral of a function. It is an approximation to the integral of a function. So while we have not integrated this function, we have found an approximation for that. That's what Taylor polynomials were all about. All right, that's going to do it for differentiation and integration. And in the last video, I'm going to talk about multiplication.